Hi everybody. In this video, I'm going to introduce to you the formula for the force of gravity and a few other terms that you need to know. So first off, let's start on the moon here. This is a picture of the surface of the moon from NASA. NASA was able to put astronauts on the moon back in the 60s and 70s. And if you've seen any video clips of those, they look like they were bouncing around, or they look like they were very light. And that's because the gravity they were experiencing from the moon is a lot less than the gravity that they would experience from Earth. So how strong the gravity from the moon is, or from any planet for that matter, or moon, can be encapsulated by this term here called the gravitational field strength. The gravitational field strength. The letter we use to represent that is G, and that's defined as the amount of force per kilogram applied to objects. The units of that would be newtons per kilogram, because force is measured in newtons, and it's force per kilogram. Okay. For the moon, that number turns out to be approximately 1.6 newtons per kilogram. So that means Neil Armstrong and Buzz Aldrin and the spaceship that they took there, all of those objects on the moon experienced a force of gravity pulling them down. And for every kilogram, I'll just use Neil Armstrong as the example, for every kilogram that Neil Armstrong was, he would experience 1.6 newtons of force due to gravity. So there's Neil Armstrong. Let's just say he's 80 kilograms. So how much force of gravity does he feel on the moon? Well, we would actually just take 80 kilograms multiplied by the 1.6 newtons per kilogram, and that turns out to be 128 newtons. And I'll round that to two significant digits. That makes 1.3 times 10 squared newtons, and the direction would be down. So what's going on is that the moon creates this whole force field around it, all over its surface. We call it a force field, the gravitational force field. And any time an object enters that force field, such as an astronaut, that force field is going to cause a force of gravity on that object. And the amount of gravity is just going to be 1.6 times however many kilograms that person is. Okay, that's the number for the moon, and it's different for other planets, and we'll get to that. So here's the formula for the force of gravity. Fg is a symbol for the force of gravity. It's a vector, but I have magnitude bars around this. So this formula just gives you how many newtons it is. The direction of the force of gravity would be down when you're on the surface of the moon or a planet. Okay, so this formula is simply saying to find out the force of gravity, you multiply the object's mass by G, the gravitational field strength. The units would be kilograms for mass, newtons per kilogram for gravitational field strength, and when you multiply those together, kilograms divided by kilograms cancels out, leaving you with newtons. And that's what we have on the left side. We have newtons. All right, so one piece of terminology so far is gravitational field strength. The next piece of terminology I want to try to teach you is the word weight. We use the word weight in everyday language. However, in physics, that word has a very specific meaning. So when you're doing problem sets or tests or anything that's going to get marked, you need to be careful that you're not using this word incorrectly, that you actually use the physics version of it. So in physics, the weight of an object refers to the force of gravity acting on it. The weight of an object refers to the force of gravity acting on it. So weight is a force. That's what I'm trying to say. Weight is a force, and forces are measured in newtons. So here I say weight is measured in newtons, and that's different than mass. Mass, on the other hand, is measured in kilograms. So there's a difference between those two words. Do not use them interchangeably in physics. For Neil Armstrong's example, we would say that Neil Armstrong's mass was 80 kilograms, but his weight on the moon was 128 newtons. Mass is in kilograms, weight is in newtons. And now I'm going to bring Neil Armstrong over to Mars. Now, we've never landed humans on Mars yet. We've landed rovers there, so robots just going around the surface. But let's just say we brought Neil Armstrong to Mars here, and he's 80 kilograms. So the question says, if 80 kilogram Neil Armstrong weighs 297 newtons on the surface of Mars, what is the gravitational field strength on the surface of Mars? So we have to find the value of G for the surface of Mars. The value for the moon was 1.6, and now we have to find the value for Mars. And I expect that number to be higher than 1.6 because Mars is bigger than the moon. So how do we find that? Well, we're going to apply our new formula for this lesson. Force of gravity equals mass times G. And our goal is to find G. So I can do that by rearranging the formula, divide both sides by m. That gives me G equals force of gravity divided by the mass. And then I can fill in the values given at the top here. 297 newtons is the weight, or the force of gravity, goes in the numerator. 80 kilograms goes in the denominator. And then I divide, giving me 3.7 newtons per kilogram. 3.7 newtons per kilogram. I really emphasize the units there. The units for G, gravitational field strength, are newtons per kilogram. So that's more than twice as much as the moon. The moon was 1.6 and Mars is 3.7. So what about the Earth, right? What about the Earth? So this is a picture of Maxwell Heights, which is on the Earth. This is the number we really want to know because most of our problems are going to take place near the surface of Earth. I did not start with Earth. I started with the moon and Mars because I wanted to get the language across to you and the concepts across to you. In terms of gravitational field strength, what that means, and what weight means. But the number you need to know for Earth is a number you've seen before, 9.8. Okay, 9.8 newtons per kilogram is a gravitational field strength near the surface of Earth. That number matches the acceleration of any object due to free fall. Okay, we did that a whole lot. In Unit 1, we had objects, they fall down. Okay, so when I let go of the pen, it starts at rest. It starts at 0 meters per second, and it speeds up. And for every second it falls, it gains an additional 9.8 meters per second. And that's not just for the pen, that's for any object that I dropped in the classroom. When we ignore air resistance, that is, they all accelerate down at 9.8 meters per second squared. And that actually is because the gravitational field strength of the Earth is 9.8 newtons per kilogram. Okay, so that was an introduction to the force of gravity and the formula for it. What you need to do is the Google form that has a few questions to check your understanding and to check in with me. And then in the next lesson, we'll start doing some problem solving with this formula. I'll see you then.